at section 6.2 or 8.2, depending on which curriculum you're in. And we are continuing on from what we discussed previously in the last section. So this will be the same concept. It will be looking for intervals where the mean, the population mean, and we will, in this time, we will not know the population standard deviation. So sigma is unknown. Let's again remember that's the population standard deviation. So what we are going to do is today we will be using the t interval rather than the z interval. And we'll see it works similarly but slightly differently. And so we're going to go look a little bit of theory of what the t interval is. The t is a very similar type curve but slightly different, which allows us to make progress getting the confidence interval using, we're going to see here instead, so we will do the t interval. With the t interval, what we end up using, since we don't have the population standard deviation, we will be using the standard deviation from the sample. So there will be some adjustments needed. We will be able to list the sample size. We still will use the sample mean. That was similar to what we were doing with the z interval. And the new part is instead of having the population standard deviation, we only have the sample standard deviation. Okay. So one of the ways we are able to do this is with that adjustment to the standard deviation of the sample. So S, remember, is a standard deviation of a sample. And look at this again. We divide it by the square root of the sample size, much like we've been doing every time since that section on sampling error, right? So this is what's going to get used. In our calculators, it'll handle all these details, but I'm just making clear to you all the formulas and the process that we go through. One of the things we need, the t-distribution is specifically designed for samples less than 30. So that 30 is sort of like that magic number. If there are 30 or more, we can use the z-distribution. But the t is specifically for less than 30, and the variable is approximately normally distributed. So that's important. We can use this t-distribution. And one of the key things in this, though, is that the population standard deviation is unknown. If we know the population standard deviation, then, and all this other stuff is true, we can use the z interval if known. If it's not known, then we will use the t-distribution of the t interval. Okay. Okay, so this was from the last one. All right. So here's just some general properties of the t-distribution. We'll see there's three properties that are similar to the z-distribution that we've been using, the normal, standard normal curve. First of all, the mean, median, and mode are all equal to 0, right there in the middle, just like the normal curve. The t-distribution is also bell-shaped, and it's symmetric about the mean, just like the normal curve. The total area under the t-curve is 1. Again, these are all the same, just as we've been doing. But here are some of the differences. So one difference is that the tails of the t-distribution, that they're a bit thicker. There's more in there on the tail side than the standard normal distribution. The standard deviation varies with the sample size, but it's always greater than 1. But that's why we're going to be looking at the sample size. As the sample size changes, so does the adjustment to the standard deviation. Remember, we are dividing by the square root of n, so the standard deviation itself will change with the t-distribution. Also, what we see with the properties of the t-distribution is there's something that we refer to as degrees of freedom. We're going to have to state this, and this really is just, it's always going to be 1 less than the sample size. The way to think of this, what degrees of freedom, basically to calculate the mean of the sample, that takes up one of the items from the sample, right? So if we had 20, we use up 1, we'd have 19 left to sort of be free. So that's what the degrees of freedom are. We had 20 in our sample, subtract 1 from that, we would have 19 degrees of freedom. It's always just 1. Again, the calculator will take care of this when we're doing our calculations, but we just want you to be aware of that. Also, the t-distribution has a similar sort of shape, as we said, it's symmetric about the mean, median, and mode, which are all the same. And but there's, depending upon the number of degrees of freedom, there's slightly different shapes because of the standard deviation change, all the way up to 30. But if we have 30 or more degrees of freedom, it's so close to the standard normal, we can just use the standard normal in most cases. So again, that sort of magic number of 30. Okay. So one of the things we do have is the critical value. And we can look this up in a table, or our calculator will also address this. So let's go ahead and dive into how we're going to be using the table. So again, this topic we're talking about are inferences. So we go there. We are doing intervals. Tests are in the next chapter. And we are still working with one mean. We will use these other ones, proportions and two means and such, later. And this time we are going to do t intervals rather than z intervals. Okay? And once we come here, we can input our statistics. There's a place to input the sample mean. There's a place to input the sample standard deviation. Notice this is different. It's not the population standard deviation, just the sample one. But we're just going to leave these at the default for now. I'll come back when we actually have a full question. We'll do this, but I'm going to show you that if we just enter the sample size of 15 and the confidence level of 95, which is the default, that when we go to the next one, we get our critical value for t, 2.145 if we round that. You could also, like from the old days, this is how we did it. We had a table, and most textbooks for statistics still contain these tables. You'd have to say, okay, sample size 15 minus 1 gives us 14 degrees of freedom, and we're looking at a 95% confidence interval. And so where those two meet, look down, is 2.145, exactly what we came up with here. Our calculator will handle the details for us, so we're not going to bother with the table. Okay, so t interval, and we can enter the details as far as the size of the sample, and we'll be able to look that up if need be. it will give us, once we enter in these, the mean and the sample mean and the sample standard deviation, we will also get the margin of error, the sample error, standard error, and be able to get the confidence interval. Okay, so basically we end up using it the same as we did with the z-interval. There's a 95% confidence interval, and that leaves 2.5% on each of the tails, and there's our critical value. Okay, so let's do an example. First of all, we are randomly selecting 16 coffee shops. So notice that's going to be our sample size. It's less than 30. And measure the temperature of coffees sold at each. The sample mean is 162 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. Construct a 95% confidence interval for the population mean temperature code. Assume the temperatures are approximately normally distributed. So that's important. We need that. So we do have less than 30 in our sample, and we do not know the population standard deviation. We only know the sample standard deviation. This is a perfect example of where we need to use the t distribution. And the way we go about doing that, let me back up all the way, right, to inference. Go to intervals. We're looking for the mean, only one mean, and we need to use t-interval because, watch with z intervals, you need the population standard deviation. We don't have that. Can't do this one. So we back up, we go to t-interval. Input our statistics. We do have the sample mean, that's 162. We do have the sample standard deviation, that's 10. We have the sample size, that's 16. And the confidence interval is 95, which is the default, so we can just accept that. We have our critical value. Again, that would be used in the formula, although this is all embedded. It calculated both the standard error and the margin of error for us. What we're going to see is that margin of error is used with the temperature, the mean, sample mean. So 162, back up, sorry, 162 plus or minus 5.3. There's our margin of error. However, if we go one more step, notice 15 degrees of freedom because 16 minus 1 is 15. We actually get the confidence interval here, 5.32, all that out there. Our confidence interval is going to be 156. And since we've only got one decimal place on the mean, let's only use one decimal place here, and then 167.3. So what we're saying is that the population mean is between these two places. We have a 95% confidence that the population mean is between these two values. Okay, so that's what's being given to us right here, and we're seeing it's a 95% confidence interval, taking the mean and adding and subtracting the margin of error. So out, and we'll see here on the next slide, that's exactly what they did, the values that they came up with on their confidence interval using formulas. I wanted to emphasize, I took those out though, wanted to emphasize of how we're going to use a calculator as we've been using before. Okay. Here's another example. So we randomly select 36 cars, so that's a sample size. Same models that were sold at a car dealership, and determine the number of days each car sat on the dealership slot before it was sold. Sample mean is 9.75 days. Again, that's a sample mean with a sample standard deviation of 2.39 days. Construct a 99% confidence interval for the population mean. Uh, in the first couple weeks, we made a big deal about whether something came from a sample or a population. And at the time, it may have seemed like that. Why is that so important? Well, now we're seeing its importance to tell the difference between these because of the behavior in a population with a much, has a much larger number in the population than in a sample. Uh, this one, since there's 30, more than 30 or more in the sample, we might be tempted to go ahead and use a z uh, interval. However, we don't have the population standard deviation. We only have the sample standard deviation. So in this case, we are also locked in to using a t interval. Okay. But we can calculate this t interval. We'll input the statistics. The mean we're given is 9.75. The standard deviation for the sample is 2.39. And the number in the sample is 36. We want a confidence interval of 99%, 0.99. We go to the next. Again, we've got all these details that can be useful when doing the calculations. I'll show you that in just a moment. But the calculator uses all of that and comes up with our confidence interval of the sample mean 9.75 plus or minus 1.08. And actually, yeah, even if you round to 1.08 or 1.084, 1.8085, right? But again, they'll give us the confidence intervals here, start to the end. We've got 2 decimal places, so let's use 2 decimal places in this. 8.67, rounding that one. So the population mean is larger than that, and the population mean would be smaller than 10.84, rounded to 2 decimal places. So there's our 99% confidence interval that the population mean is between these two values. And on this slide, I have detailed out the screenshots that shows you what to input to do these so that you can see how to navigate to our final answer step by step. What they've done, the standard way of doing things, is I'll use this formula to get the standard error. And so the critical value for t, they had to find that. They took the standard deviation from the sample, divided it by the square root of the sample size, and all that's multiplied out. They got about 1.09, slightly more than we had, probably slightly a rounding error in there because they're only using 3 decimal places. Remember, our calculator carries through all the decimal places as it goes through. However, in the end, they got fairly close to what we had, 8.66. Ours got rounded up to 8.67, and we got the same thing here, 10.84. Okay, so we may face slight rounding errors, but we're right on track there. What I wanted to show you here is the value of the technology we're currently using. It provides a graphical view of this confidence interval. Here's something called StatCrunch. You would have entered in the same information, and this is a little report it gives you back. It give you the standard error. It doesn't give you the margin of error, and while it gives you the lower limit and the upper limit of the confidence interval, it doesn't actually. See, if they went with this, you'd round that up. I'd go 6.7, just like we did. And there, so a little bit different. But anyway, it doesn't show the graphic of what's going on. So I just want you to see what we're doing. Now here's a diagram that helps us to know whether to use the z. This would be a z interval. and this is going to be the t interval, the new one, what we're doing today. So first of all, for both of these, the population needs to be normally distributed or has a sample size greater than 30, one or the other. If neither of these is true, you cannot use the standard normal distribution or the t-distribution, right? So one of these has to be true. If it is true, then the question comes down to, do we know what the population standard deviation is? If yes, then that's when we use the z interval or the normal, right? If no, that's when we use the t. Okay, so again, slightly different formulas. For us, the difference comes from, let's see if it clear out the writing. The t interval, we just choose that from the calculator tool, and then we input the sample standard deviation because that's what we have. If we're doing the z-score, the z interval, we ask for the z interval, and then in the statistics that it asks for, we are able to enter the population standard deviation, which is actually a parameter, right? Because it's coming from the population. So those are the two differences that we have. And this last question, we just want to ask, which could we use? Could we use normal or just t-distribution, one or the other? So we randomly select 25 newly constructed houses. So the sample size is less than 30. Okay. The sample mean construction cost is $299. So there's a mean. And again, that is always going to be given to us as a sample mean. And the population standard deviation is 46,000. That's a population standard deviation. Assuming construction costs are normally distributed, which is important for both of those, should you use the normal distribution or the t-distribution? Well, it's okay that we're under 25 as long as we're normally distributed, but since we have the population standard deviation, the one we're going to go with is the normal distribution, right? Because again, on our calculator, if we're doing the t-distribution, which is this one, there is no place to put the population standard deviation. It's only a place for the sample. If we keep going back and we go to the z interval, that's the place where we can put in the population standard deviation. That's pretty much it. And that's the last slide. So you'll be able to do the homework in 6.2, which will primarily be looking at t-distributions, but always take a look at the question and be willing to say, you know, there might be one or two in there that you need to use a z-distribution. And again, it all comes down to this very powerful thing of whether the standard deviation we have is from the population or the sample. If it's from the population, we're going to do a z interval. If it's from the sample, standard deviation, then that's when we use a t interval. Very good. Thank you so much.